Second recording this video for me because my head hit the microphone again, just like when we did that online session and the sound went off. So here we go. Figure 6 shows the negatively charged metal dome and an earthed conductor. So if it's negatively charged, okay, the earthed conductor is going to be positive relative to it, which means there is a potential difference between the two. Okay, and this is really important. That's why if you touched it, okay, the negative dome, there'll be a potential difference between you and the dome, which means you'll get electrocuted. Okay, and that's because charge will flow through you to the ground. So this is really important. This is not a calculation. This is just as if you ever get asked if you ever get asked in your exam why you get electrocuted. So you get electrocuted because there's a potential difference between person and live object. Now any object that's charged we call is live. So that's charged, so it's a live object. Current flows through object to ground when in contact. Okay, so if it's in contact, it flows through object to the ground. Okay, and in doing so, current flowing is an electric shock. Flowing through something is an electric shock. And that's how you get 3 marks in that sort of question. So well worth working out, okay, and remembering. Right, so here it says, when the earth conductors move towards the metal dome, there is a spark between the dome and the earth conductor. The spark transfers 0.6 joules of energy and 2 microcoulombs of charge is transferred from the dome to the earth conductor. Calculate the potential difference between the metal dome and the earth conductor. Use the physics equation sheet. So we have to use the physics equation sheet, and we have to use C-FIFA with every single one of our calculations. Now remember, this is worth 4 marks, so it's almost certainly only going to require 1 equation. Now we do need to do some converting, so that's the first thing we do. We convert. We need to convert that to coulombs, because it's microcoulombs. So what we do is we remember our ultimate weapon. So we start with our square, and if we go in this way, because it's our smaller one, it's going to be millicoulombs, then it's going to be microcoulombs, then it's going to be nanocoulombs, and it's going to be picocoulombs. And remember the pattern, 10 to the minus 3 times 10 to the minus 6 times 10 to the minus 9 times 10 to the minus 12. Now we want microcoulombs, which is that one, and it's 2. So it's 2 times 10 to the minus 6. And we just keep it like that. I wouldn't bother changing it to numbers because that's something that's just an extra step you don't need. And that will get you one of your 4 marks. Okay, easy. Now we want the formula. We want something with potential difference. We want something with energy. So we want something with energy. We want something with charge, and we want something with potential difference. Okay, so we keep going down our list. It's to do with electricity, so it's going to be anywhere from here to here. So we've got charge, we've got current and time. So charge is there, but we haven't got anything else, so it's not that one. We keep going down, it's none of these. Okay, we've got charge there. Remember, charge and charge flow are the same thing. Potential difference is there, and energy transfer. So it's definitely going to be that one, okay, because it has all 3. So we write equals E equals Q times V. Q's for charge, V for potential difference, E for energy. And then we insert our numbers. Okay, so our energy is 0.6 equals, our charge is 2 because it's the new one, remember, that we've converted, 2 times 10 to the minus 6, okay, times by our V, and that's what we want to work out, V. So now we need to rearrange that, and we need to get V on its own. Now because we're timesing V by 2 times 10 to the minus 6, we get V on its own by dividing by 2 times 10 to the minus 6. And whatever we do to the right, we do to the left. So it works out as 0.6 divided by 2 times 10 to the minus 6 equals V. Because remember, we get rid of that by dividing by 2 times 10 to the minus 6. And whatever we do to that side, we have to do to this side. So we end up with that. All right. Then, if we put that into our calculator, 0.6, make sure you use the fraction button, divided by 2 and then we do times by 10 to the minus 6, and then we press equals. That gives us 300,000 volts, which sounds like a lot, but it has to be a lot to cause a spark. Okay, so it's 300,000 volts, and that's correct. The voltage will always be high for a Van de Graaff. It'll always be a really high voltage, but not much charge flows because it sparks for a fraction of a second. So that's why if you were to get electrocuted with a Van de Graaff, it wouldn't cause any damage to your body, or very unlikely to, because it only sparks for a fraction of a second. All right, it doesn't continuously flow through your body.